multiplied by a 1, because that 3 means the third derivative, not a third power. So it's this one, right? So this is why it's not linear. How about the last one? And so the last one is linear. Right? Now, usually this is where students get sort of confused. Oh, there's an x squared multiplied to your y. Well, y is what you're focused on. So since x squared is going to be considered a constant here, or at least a non-y variable, and so this appears as linear expression, right? So this is actually a linear equation. Okay. Any questions on this? Any questions on it? Any questions on linear, non-linear, order differential equations? Now, this part becomes a little bit important, at least on the first section that we're going to do, which is in the first section, first couple of chapters, so chapters 1 and 2. Because when we start solving differential equation, at least the first order differential equation, we're going to have a different method if it's linear. So if it's linear, we're going to approach it a different way. So we are going to have a method exclusively for linear differential equations, and then we'll have a separate one for the others. But so that means you have to know if an equation is linear, right? So if you spot it's a linear differential equations, then you can apply the method that we're going to go over, and then just simply get your answer from there. Okay. Any questions on these? Okay. So now, if there are no questions, so moving forward. Okay. Okay. All right. So now, speaking of solutions, right, or solving. Okay. So solving, remember, is a solution or finding solutions to differential equations. So we need to talk about solutions, right? So example number 7. Okay. So obviously the solution to your differential equation is a function, right? Because that's what you're trying to find, right? So you're trying to find a function whose derivatives satisfies your differential equation. So suppose my differential equation is this. So dy dx is equal to 3y. Right? So is y equals 2e to the 3x a solution? Oops, question mark. Well, how do you do this? Well, it's the same way you check any solution you've done for any equation you've seen before. The way you do it is you plug it in and see if the equation balances out, meaning the left side equals the right side. So all you have to do is plug it in to both sides of your equation. So on this side, you're just simply going to plug in your y. On this side, you have to plug in the derivative. So which means, what is dy dx? So what's the derivative of y? It's 6e to the 3x. Okay. And then now plug it in, right? So again, I'm going to show pretty much all my work for now because it's the first example. So dy dx is equal to 3y will now be 6e to the 3x is equal to 3 times 2e to the 3x. And then working both sides, you get 6e to the 3x equals 6e to the 3x. It balances out, so which means it is a solution. Okay. Questions on that? Any questions on it? Okay. So I want you to try this one. Okay. So number 8. So my differential equation is as follows. So y double prime minus 2y prime minus 8y is equal to 0. Okay. And this time I want you to check a few functions here. So y equals e to the 4x. Okay. Y equals 3e to the negative 2x. Okay. And then the third one, I want you to see if the sum will be a solution. Okay. So you're going to do this 3 different times and tell me if each one of these are solutions. Okay. So again, I'm going to pause it. Right, please no recording. All right. So going back to these before I actually show the work, are which one of these are solutions? First, second, or third? All of them. Right. So all of them are solutions. Okay. So let me first show the work. Okay. So on the first one, right? So y is e to the 4x. Okay. And then y prime is 4e to the 4x. And then y double prime is 16e to the 4x. And then now plug it into your differential equation. You have 16e to the 4x. That's your y double prime. Minus 2 times y prime, which is 4e to the 4x. Okay. And then, sorry, minus 8. So minus 8e to the 4x. And you want this to equal to 0 because that's what you have. And then just see if it actually adds up to 0, right? So 16 minus 8 minus 8, you do get 0 equals 0. So the first one checks. Okay. And you basically do this for each one of them, right? So for the second one, it's 3e to the negative 2x. Y prime is negative 6e to the negative 2x. And then y double prime is a positive 12e to the negative 2x. And then plug it in. So you get 12e to the negative 2x minus 2 times negative 6 e to the negative 2x, and then minus 8 times 3 e to the negative 2x is equal to 0. And so you get again 0 equals 0. So it checks. Okay. Now the third one is just really just checking to see if it is going to be the same thing. And since the first two sort of works, it's just going to end up being the sum of those two. And you know it's going to work at the same time as well. Okay, so the third one's going to work as well. Okay. Any questions on that? All right, so a couple of things on here, right? So there's a reason why I asked this question. So one is your solution is not unique, right? So it is not unique, okay? So there's more than one answer, okay? And so this is sort of where your linear algebra sort of mixes with your differential equations. And so what we have formed, or essentially what we have is if we have a differential equations, or differential equation, sorry, we have what we call a solution space. It's a vector space that contains all the solutions to your differential equation. And much like any vector space, we are interested in determining, finding a basis for that said solution space. And so we're going to learn how to do that, obviously, when we move on. I think it's chapter 3 or 4, where we actually do an nth order differential equation. And that's where your linear algebra starts mixing in with your differential equations. Okay. Any questions on these? Any questions on it? All right, now there's just one last thing on really those two sections, 1.1 and 1.2. It's sort of the initial value problem. Which is called IVP. Okay. Versus boundary value problem. Okay. So initial value and boundary value problem. Okay. And so here are examples of each one, right? So um, initial value. Okay. So we have so like x double prime plus a 5x prime plus a 4x equals 0. And then we have x of 0 is 1, x prime of 0 is 2. Okay. So it's called initial value problems because the initial condition is applied on a single sort of value. In this case, it's where the independent variable, which we'll probably call t later, so t is 0. Okay. The boundary value problems sort of almost looks like this. You're evaluating your functions for your conditions, okay, on two different x values. And that's the difference between initial value problem and boundary value problem. Now, it might look like a sort of small difference, okay, but there are methods for more complicated differential equations in which you have a different method for this one compared to this one. Now, as far as our class is concerned, we're only going to be dealing with initial value problems. Okay. So, any questions on these? Any questions on your definitions, introductions? All right, so I think it's about time to take a break right now. So let's go ahead and take a 10-minute break, okay? And then we're basically done with 1.1 and 1.2, okay? And so the next one now is we're gonna start actually solving differential equations, okay? So let's go ahead and take a 10-minute break. Okay. Let me pause the recording.